Okay, so I hope nobody else is having any problems with the lecture notes on the website, because I couldn't figure out what was wrong with them last time. They seemed to work for me. But anyway, let me know if there's something wrong, and I'll try to fix it. We have some announcements. Homework 1 is still due this Friday. There are lab sections this week, so if you're in a lab, you can go to your lab. And then there are still 2 more of these optional C++ mini tutorial things that are happening. The one that's happening tonight is in this building in room 2. This is room 6, I think. So, and then Tuesday, it's in the Learning Center in room 182. How many people went? Just to get a feeling. Was it good? Yeah? That's what I figured. I should probably go. Okay. Any questions about announcements? Yeah.
Will we have a programming assignment next Friday?
No. No. No, there won't be a programming assignment due next Friday. I'm still writing the first programming assignment. It's going to be great. It's so cool. It's fantastic. But it's not quite done yet. And the minute that it gets done, I'm putting it up. So I'll put it on the web and I'll tell you about it in class and that it's there. But it won't happen for about maybe 2 more days. Maybe 1 if I'm really... I mean, it's working. It's just that I haven't written any of the stuff. You know, the words. Okay. Any other questions? Okay. We are going to talk a little bit more about runtime, and then we're going to talk about program correctness for today. And so as a warm-up, this is a warm-up for today. You should look at this piece of code and figure out what is, first of all, what's a better name for it than food? And then secondly, descriptive name. And then secondly, what is the running time? So I'll let you do that for just a second, or maybe you've already done it already, but let's just do that for a minute, and then we'll talk about it. You can talk to each other, you can spin it around, you can do what you want. Okay, everybody set? Everybody got this figured out? And of course, your first statement is, I don't know what you're talking about now. But let's start with better name. What's the better name for this sentence? Yeah.
First value.
First value, that's a good one. First value. I don't know what I called it, but first value is better than that, than what I had. First value. What is the running time? Now, you already know running time should be a function of the size of the input. And I haven't told you whether we're talking about worst case, best case, or average case, but let's just say worst case, because pessimists. And what is the worst case running time of first value? Yeah.
That's the length of the array.
It's the length of the array. The running time is, you want to say something like the worst case big O of n. Yep. You want big O of n, or what would you like?
Big O of n. Okay.
That's good? Okay. Everybody happy with that? Big O of n? Anybody not happy? Big O of n. One person is not happy. Two people. 3, 4, 5, 6, 7, 8, 9. Holy cow. 10, 11, 12. Uh-oh. You're not happy with big O of n? Why not? Why not? You.
It'll just run through it once.
Yeah. It's going to execute once. It's going to go through and say, is I equal to 0? Yes. And it'll return array I. Or if it happens to be the case that the length of the array is 0, it will fall out immediately and return -1. So, is the running time big O of n? People think no. Do you remember the definition of big O of n? It's less than or equal to some constant times n for all values of n bigger than something or other. So is a constant less than or equal to some constant times n for all values of n bigger than or equal to something? Yes? Sheepishly? Because if it's true, then this running time is big O of n, and you are absolutely correct. The running time is big O of n. It's like I planted it in the audience. Because this is what I wanted to teach you, is that a running time, if it's big O, it's an upper bound on the running time, right? Now, it is true, but it's not tight. Not tight. By the way, I changed the size of the pen. If you like the new size, that's good. If you don't, I was thinking that it might actually help my writing, so we'll see if it works. Anyway, comments are appreciated. This is true, but not tight. What is a tight bound on the running time? Now, what does tight mean? Well, tight means it's an asymptotic bound, and it's the best that you could find. It's the best, the smallest upper bound that you could find. The smallest function such that the function is big O of that function. Or if you're really lucky, you could actually say that it's not only big O of that function, but also big omega of the function. It's bounded above by the function. That's a big O bound. And it's bounded below by that function, or constant times that function. That's big omega. So what would be a tighter bound for this? Yeah.
Small O.
No, small o is different. Small o is strictly less than. So it is true that this running time is small, little o of n, because it is less than or equal, it's less than n for all constants, c times n, for large enough values of n. So, frankly, we're probably never going to talk about little o or little omega in this class, except we already have. But I'm thinking about big O and big omega, and big theta, which is when it's both. For this code, what is its running time as a tight bound, an asymptotically tight bound on the running time? Now you're a little gun shy because you're already like the people that said, no, it's not n, it's something else. Now they're feeling like, but you're right. You're absolutely right. Don't be gun shy. You right back there. 1. Excellent. The running time is also big O of 1. It's less than or equal to some constant times 1, because it's a constant, some constant. 2, maybe 2 lines of code are executed. Maybe 3. It's also big omega of 1. That means the running time is greater than or equal to some constant times 1, because the code is actually getting executed. It's executing some, maybe 1 or 2 lines. It's greater than or equal to some constant times 1. So therefore, these two facts imply that its running time is theta of 1, which means that 1 is a tight asymptotic bound. Theta of 1 is tight. It's big O and it's big omega. It is not true. This is not. Whoops. it is not, so the running time is not big omega then. It's not greater than or equal to some constant times n. Okay? Fun with asymptotics. Any questions about this? Because this is kind of the way we're going to talk about code and running times. Okay. Here's the code that we were talking about before, the linear search code, which had a running time t of n, which was 2n plus 1. And the last question that we didn't get to last time was, what is the appropriate order notation to use for describing this running time? We already proved on the previous, like last time, that this is big O of n. But we also know that there are other order notations like big omega, big theta, and little o and little omega. What's the appropriate order notation for this running time, to express this running time to somebody, to tell them about it? Should you say it's big O of n? When would you want to say that? Suppose you wanted to tell somebody that this was a really fast algorithm. You wanted to claim that this is a good algorithm. You wanted to tell them some good news. I have this great algorithm. Let me tell you about it. What order notation would you use? The whole question basically depends on the story that you want to tell. So what I wrote down in my notes is what spin. So what spin do you want to put on this running time of 2n plus 1? Do you want to spin it positively, or do you want to spin it negatively? Positively, you're saying it's good. So if you want to claim the algorithm is fast, what order notation would you use? If you claim algorithm is fast, what would you want to use? I'm going to claim it's quick. Yeah.
Big O, because you can just say big O of n and c times n can be greater than 2n plus 1, and it shows that it's smaller, where it's encapsulated in big O of n, which makes it look faster.
Yes. I will repeat what you said using maybe less and different words. But that's exactly right. If you want to claim the algorithm is fast, use big O. Because you're claiming now that the running time is less than some function. In this case, the function is n. You're claiming the running time is less than n. So when you tell me that the algorithm is running in big O of n time, you're telling me it's fast. It's quick. It's less than n. Less than some constant times n. If, on the other hand, you wanted to claim that the algorithm is slow because you happen to know that this linear search thing is just terrible. It's so slow. Linear search takes forever. Why would you want to do linear search? Why don't you use logarithmic search? Why don't you get a quantum computer and do search in square root of n time? Wow. Can you do that? What would you say if you wanted to say this algorithm, the non-quantum algorithm, is slow? You'd say its running time is bigger than something, yeah?
Sigma or the horseshoe shape?
Yeah, horseshoe shape, omega.
Omega.
You actually are not in a fraternity or sorority, are you? No. It's like they put you in those things and teach you Greek. Anyway, omega of n. The claim is the algorithm is slow. Omega of n. The running time is greater than or equal to some constant times n. Okay? You got it? This is all about asymptotics for expressing running time. Look, let me tell you something secret. Nah, it's not secret. People like me write papers about this sort of stuff, algorithm analysis, and we will occasionally claim that somebody's algorithm is slow using big O notation, and nobody kills us. Nobody comes and hunts us down, but it's wrong. I can't say that your algorithm is poor because it's a big O of n squared algorithm. That's not an argument that says it's a bad algorithm. If I said it was big omega of n squared, then that's an argument. But it happens even in the papers that I write, well, not the ones I write, of course, but sometimes in papers like this that they'll switch, they'll use big O all the time instead of using big omega, for example, for lower bounds. Anyway, I'm trying to get you to see that there's a difference, and it's important. Okay, now we've analyzed code. This is a summary of how to analyze code. Single operations take a constant amount of time. So when you're looking at a piece of code, you want to tease out what its running time is. You have to do sort of certain things depending on the operations. Like consecutive operations, you sum the operation times. Conditionals, you take and you count the branch depending on if you're a pessimist or an optimist. If you're a pessimist, you find the max length branch that could be taken. So if there's an if clause, you believe the worst. And then loops, you sum the loop body. So if you have a loop, there's something that's going on inside, you have to sum that up. If the loop contains a loop, then you have to do the inner loop, figure out how much it takes, and then sum that for the bigger loop. So you have to count all the stuff that's done inside of loops as they go through. And then if there's a function call, you have to count the time for the function call because that function call is actually going to, who knows what it's going to do. It takes a long time to do stuff. You have to count that and add that onto the running time of your code. Really, what you're doing is you're just being a computer and trying to figure out what steps are being taken by the computer, and so you just use your head. That's really the thing to do. That's the summary of it. Okay, and here are some words for you. These are words that are used for talking about running times, constant, logarithmic, polylog, linear. Nobody ever says log linear. Superlinear, quadratic, cubic, polynomial. And then there's a divide here, as we saw in that first slide of running times when after you wanted to solve a problem of size 100, which was taking 2 to the 100th time, it basically took you like 32 billion years. You take a step from polynomial to the intractable running times, which are exponential. Exponential are like c to the n for some value of c. So this is what is it, a taxonomy, a dictionary? It's a list of names for different types of commonly occurring running times for computer algorithms. So you can say, I have a quadratic algorithm for comparing genomes. And people will say, wow, that's going to take a week. Ugh, I don't have a week. Figure out some sort of n log n algorithm. They won't say log linear. They'll say n log n. Okay. By the way, here's something to ponder. Is 3 to the n theta of 2 to the n? They're both exponential. Anyway, you can figure that out. Where am I? By the way, I'm trying to be a little bit quicker. If you don't like it, let me know. But I'm thinking like things might be a little slow. Just for my own entertainment, how many people think this is true? 3 to the n is theta of 2 to the n. It's basically some constant times 2 to the n. How many people think that that's true? Nobody? Oh, a couple people. Few people think that this is true. This is true. It's theta of 2 to the n. There's some constant times 2 to the n such that 3 to the n, well, we know that 3 to the n is bigger than 2 to the n, so we don't have to worry about that. We have to worry about is there a constant such that 3 to the n is less than or equal to a constant times 2 to the n for all values of n bigger than something. What could that constant be? It doesn't exist. It's not true. Okay. We're switching from running time, which we now know everything about, to proving program correctness. So here's a piece of code which has no name, because if I told you the name, then you know what it did. And I want you to figure out what it does, first of all, and then is it correct? And if you come up with what it does and is it correct, then you can let me know, okay? Or call on somebody to let me know. So you talk amongst your neighbors, figure out what this thing does and whether it's correct. Or not. Maybe you're a little shy about doing this because there are some things about this that are different than the algorithms I've shown you before. This one is written in C++. Do you guys know what that symbol is? This is pass by reference. It means that instead of copying the array of strings A, the vector of strings A, instead of copying that when the function is called, the function just takes a reference to that, which means that any modifications that this function does to that vector are permanent. They affect the caller. So somebody called this function, that's the caller. They passed in a vector of strings, and this function, because it gets that array, that vector by reference, this function, when it changes the vector, it changes the caller's vector. It doesn't make a copy when it passes. But it has absolutely nothing to do with the running time or what this function does, except that it's just information for you to know about. That's a reference parameter. Let's pause for a second. Let's just pause for a second, and I want to take a status report. So, how much of the time that I've been quiet, which is not very long, but how much of the time that I've been quiet have you been thinking about what this does? Like more than half? Like, has anybody been thinking about the running time for a really long time? Interesting. you now get the essence of it. Correctness is much harder than running time, typically. So figuring out what something does when you're not given any clue, any hint in the code, is tricky. It's not easy. But how many people have figured out sort of what this thing is doing? How many people have a reasonable idea about what this is doing and would like to share? Reasonable? How many people want more time? Like, you could figure it out if you have, like, maybe if I just be quiet. Okay, well, I'll be quiet for 1 more minute, and that's it. Okay, there's been a couple of questions about the following fact, which is the comparison operation on strings is a lexicographic comparison. So if you have 2 strings and it says, is this string less than that string, that's true if it occurs earlier in the dictionary. And the first one occurs earlier than the second one. So it's a string comparison. So what this is doing is somehow it's comparing strings from the array to do something or other. But the question is sort of, I'm actually curious to know, how did you figure out what this does if you figured out how this, well, let me ask, how many people have sort of a reasonable idea of what this is doing? Who would like to report who hasn't talked yet today? You haven't talked yet today. Would you like to report?
Sure.
Okay, great.
So we're looking at the unitary of strings, and we're only looking at the indexes that are B and the
Yeah.
And then after that, we're checking for the we're checking for the remaining strings and checking them alphabetically. And then what you return is the smallest index of the string that would be first when you order it alphabetically.
Perfect. So if you look at all of the strings from index B onwards, you're picking the string that would occur from that set of strings, the one that would occur first alphabetically. So it's, what would be a good name for this function? Something like find smallest, or find littlest, or find min. So it's finding, from starting at the index B, it's looking through this array to find the next string after location B in the vector, at or after, that's smallest. How did you figure this out? How would one go about doing that? Did you, I mean, there's options here, right? You could just stare at the code until, you know, your eyes hurt, trying to figure out what's going on. Well, what's the successful way to figure out what code does? What's the key?
Putting in some random values.
Just putting in some random values and trying it out. This is exactly the way you figure out how code works. It's also exactly how you figure out how code doesn't work. If it's failing, you put in things that are failing and you figure out what's going on. Where is it breaking down? You have to step through and execute this code on some examples. And I don't know, that's the way I did it. Well, actually, I wrote the code, so I knew what I was doing. So forget that. But that's how I would do it if I was trying to figure this out. You write down an example array of things, like something, the names of your friends, and then you run the executed on some value of b. And what it does is it goes through, and it's kind of an interesting piece of code, right? It picks up here and here. It picks up the index b, stashes it in R, and it picks up the string value of AB, and it stashes it in S. So it's sort of keeping stuff in those two special variables, R and S. And then what it does is it goes through the remainder from b plus 1 until it gets to the end of the vector A, looking to see if it can find something in the array, entry AI, for example, that beats the string S, that's smaller than the string S. So it's check if AI is better. In this case, better means smaller. And if it is smaller, then it updates the stored values that it's been keeping. It's updating R and S. So it updates if yes. So it does this initial setting, and then it just updates that setting whenever it runs into something that's smaller. And finally, at the end, it will return the index of the string that it's found, the string that's the smallest of all of the strings from b through n-1. Okay? This is great. So Feynman is a good word for it. Does it work? Is it correct? Now this is, you could say, yeah, sure, it works. It's good, it's correct. But how would you argue this? How would you explain this, first of all, in English, and then we'll do it in sort of more mathematical formalism, but how would you explain this, that it's actually making progress towards solving the ultimate goal of finding the smallest string in the strings A, B through A, n-1? So what does it do? Finds smallest string in A, B through n-1. Here n is the size. So this is what it does, or that's what it's claiming to do, and it returns the index. Yeah.
Use like induction to see that it's moving forward.
Yeah, that's exactly right. So there's a loop here, and we're sort of making progress every time we go through this loop. And we have to be able to encapsulate how that process is progressing, how that each step of the iteration gets us closer and closer to our goal of actually finding the smallest string in A, B through A n-1. So how would you say that? This is what I wrote. I wrote something down here because, I don't know, I was just trying to do something. The min so far, the smallest string is S, which is identically equal to the rth value in the vector. The min so far is S, where so far, that's two words. So far means in A, B through I minus 1. So at the ith iteration of that loop, we've looked at the beginning of the ith iteration of that loop, that's in a minus 1. We've looked at B through I minus 1 up until that point, and we're going to look at the next entry I in that ith iteration. And so up until that point, we have that the smallest, the minimum, is S, the string S. And if you think about this, I mean, we want this to be true, and we want this to keep being true throughout the entire iterations, all the iterations of the for loop. We want it just to stay true. It's what we call a loop invariant. This is a loop invariant. And we want we want, you know, the correctness that relies on this loop invariant, and so we want to actually prove that it stays true for every step of the way. So it has to be, we know it's true at the beginning, right? We know it's true before the first iteration, and we want to say that it keeps being true, it remains true over all the iterations as I increments. By the way, I encourage you to take notes about this stuff. However, if you can't read anything that I'm writing and it's really hard to understand what I'm saying and you're getting kind of like tired of doing that, the entire proof that I'm going to be doing for this is on the web page. It should be there now. And it'll be more legible than what I'm writing. But okay, so this is what we want to do, and this sounds an awful lot like induction. What we have is some statement that says it has a base case, it's true before anything happens, and then we're trying to say that it's true so far means that it will stay true for the next iteration, therefore it should be true for all iterations, and that's the whole setup for induction. And if we can prove it that way, we'll get to the bottom of the loop, and it'll be true for all executions of the loop, all iterations of the loop, including all the way up until I equals the size of the array, at which point it falls out of the loop because it fails the I less than size check. And at that point, we know that according to the invariant that we're trying to prove, or that we have proved, that the so far here, when I is equal to n, is the entire array. A from B all the way up to n minus 1 is the remainder of the array. Yep.
Also, in this case, are we trying to show that? So for this proof, are we assuming that so far is the minimum string?
No, I'm sorry. I put quotes around so far because I just didn't want you to be confused about.
Okay.
So let me erase those quotes because I confused you. Just think of it as being the minimum so far. This is like an English thing that I'm saying to you. It's like this is not precise. Well, it's pretty precise, but it's not as precise as you really like it to be, probably. I'm just saying the minimum so far is this. And then I'm telling you so far means this. It means I've gone through the loop a certain number of times. That's all. Yep.
Also, for the second, I'm saying, like, after I've gone from B to I minus 1, like, this is the current minimum value.
You mean so far means
Like,
in...
for the second sentence, like, after I've iterated from AB to AI minus 1. This AR is the current minimum value.
Yeah.
Okay.
Oh yeah, I didn't write that down. Did I write that down?
Because I just read that so far means in I minus.
Yeah, this means so far means up until some iteration I. So maybe this was not such a great English sentence to write, is it? Okay, well, anyway, if you don't like this English, read what I wrote in the big, long, giant thing on the web page, and it will be clearer. But what I really mean by this is to just say that some property, which is the fact that R and AR and well, in fact, S is the minimum string that you've seen after you've walked for a certain number of steps starting at B up until the index I, or in this case, index 1. Okay, now let's just get this out of the way. What's the runtime of this thing?
Would it be something like O n of like n m? Because where n is the size of the input vector array, and n would be like the longest string there is for the pairs.
Excellent, excellent. Okay, so the claim was it's order n m, and you have invented a new notation m for the length of the biggest string, right? Yep. So this is the length of biggest string. That's excellent. There's another parameter here, though, as well, which is b. So you could also say this is order n minus b times m, because you actually are only checking the values from b to n minus 1. And that would be good, too. This is now a 3-parameter function. We're talking about big O of a 3-parameter function, and I've only defined big O for 1-parameter functions. Are you guys happy with this? Yeah.
So if it's big O of n and m, doesn't that mean you're iterating both something of n length and something of n length?
Oh yeah, so you are, because in each iteration of the for loop, and there are going to be n of them, or n minus b of them, in each iteration of the for loop, you're doing a comparison, which is going to compare two strings. And she's saying in the worst case, you will start marching down the string, comparing character by character to the other string, and the amount of time that it will take you is the length of the string. And so her parameter here, m, is the length of the biggest string.
Right, so the m kind of comes from the if statement, where the if statement iterates through the largest string.
It comes from this operation. This takes order m time.
Oh, okay, thank you.
If I'm getting this right. Yep.
How do we find M?
How do we find m? Well, we can assume that it's worst case, meaning it could be anything. But the other thing you could do is assume that string comparisons are really, really fast and that m is basically 1. I know, you didn't like that. But it depends on the size of the strings you're comparing. I mean, if you happen to know something about that, then you can put that into this function and you can say, well, I know my strings are never longer than 100 characters. Or you can say, my strings are never longer than 1,000. But it really, getting at this a little bit more, it's the question about what is the parameter of this function that you're doing asymptotics over? What is the thing that's growing? What is the variable here? There's three of them, n, b, and m. What is the variable here that you're interested in the growth of this function as a function of? Like if I pick that, the growth of the variable as a function of that. So I have to pick, in our definition of big O, we have one parameter that's allowed to go big. And so the other parameters do not go big in our definition of big O. So one thing, and this is a reasonable thing to do in this case, one thing to do is to say that my strings have a constant length. They're not going to grow like n. The number of strings may grow, but the strings I'm going to be dealing with are all going to be short relative to n. This may or may not be true. Just like we talked about the human genome, strings could be much, much bigger than n, but maybe in this case, they are about some constant, something small, like 100. Like names in a database, yeah?
So I just wanted to confirm, like, when you say check if like AI is smaller, that means like smaller than like alphabetically.
Right,
Okay, and then like n here we're defining as like the size of the vector.
right.
Okay.
Did I write that down? I did, okay. Up here in the corner.
Oh, okay.
It's so well organized, this slide. Find all of the information on it, exactly where you'd expect. So we have to do, in this case, some sort of assumptions about what the values of n, m, and b are. And I think that the right thing to do in this case, at least it is when we are starting to apply this to other things, is to think of n as being the growth variable and m as being something that's not growing like n. It's fixed with respect to n. And b, we'll see b is going to be a parameter that will be interesting when we actually get to analyze what this function is used for. But for now, we could even just say this function is, if n and b are basically constants, this function would be order n. Assuming m and b, what I'm saying when I say assume m and b are constants is not that they're small, but that they don't grow like n grows. And the thing that we're interested in, the growth, is the running time as n grows. So assuming m and b are constant, then this is order n. Yeah. Let's see if I can do that again. Order n. Assuming m and b are constant. Okay. Holy cow. All right. We've got 1 minute left. We have the runtime. We have the correctness. We have a loop invariant statement. It's a theorem. It says that S is the minimum string in A, B through I minus 1 at the start of iteration I for all values of I in the range P plus 1 through M. So after the English, this mathematical statement sort of is kind of, yeah, of course, that's exactly what, it's almost English. So that is the theorem that we want to prove. That's the theorem that's proved in the notes that are on the web. And so maybe or maybe not, we'll get to them next time. Actually, we want to, anyway, we'll probably get to them next time.
I was wondering, like, why is it not until like n minus 1?
Just a second.